So what the team did was, let's look for a poor man's way of rapidly chilling memory chips. And so they went and got one of those cans of compressed air. Well, if you turn it upside down, the propellant is actually a liquid that I believe boils. And so by turning the can upside down, spraying the propellant directly onto the memory chips, they were able to cool these memory chips down to -50 degrees centigrade. Next slide. And the scary thing is that still worked. They were able to power that chip up and be able to read data off of it. And the effect is that by chilling to -50 degrees centigrade, they were able to increase the remnants of this memory by a factor of 100. And so instead of after 2 seconds the memory decayed, it was like 2 minutes or 5 minutes. Next slide. And so then they speculated, well, how crazy could we get? So unfortunately, there's a great picture attached to this that you're just going to have to get off their website that shows one of their PhD students bundled up, wearing, like she's on the North Pole, with these insulated gloves holding a canister of liquid nitrogen. And they used that to cool these chips to -196 degrees centigrade. And what they found was at 2/3 of the way to absolute zero, the memory didn't decay at all. You could have left that DRAM chip sitting on a shelf for a week and still get 90% of the bits out of that data, or out of that chip, basically untouched. Now, I would offer, normally I ask this at the beginning, how many computer engineers do we have here? Electrical engineers? Okay, so you guys actually deal with this stuff on a daily basis. The thermodynamic effects on electrical circuits. Well, if we can chill a memory cell, or memory cell, and reduce our refresh rate from 1,000 times a second to once every 10 seconds, we can reduce the power consumption of that circuit by a factor of 10,000. That's kind of interesting. How are we going to use that? I have absolutely no idea. But it's something to stick in the back of your mind, because as we are building computers with greater and greater performance, those types of characteristics could become very, very important. One of the Cray's higher performance computers built in back in the 90s, back in the 90s, Cray supercomputers. They were the most powerful supercomputers you could buy. They are, by today's standard, a little bit more powerful than your cell phone, which is really scary. But one of the computers that they built used gallium arsenide chips, and I don't even remember what, and it was liquid refrigerant cooling that was basically all the circuit boards were immersed in a non-conductive liquid coolant, and then it was cooled to very cold. And they were taking advantage of some of these characteristics, that these circuits ran better at very low temperatures. Anybody play video games, build your own gaming machine? Actually, I won't subject you to that. But
Chris, I want
yes,
to suggest you have to be a little bit careful with that conclusion, because even though you may change the rate, the amount of power involved in the refresh would be less than that. That's a factor, the actual power involved in refreshing data.
Oh yeah, to say nothing of the power required to cool it. That to build a refrigeration system to cool one of these circuits down to that level will consume many, many, many times the amount of power that you could possibly save by reducing the refreshing cycle chips. No, this is not, if this were a secret weapon, we'd be using it already. But they're interesting that you don't normally think about, well, how could thermodynamics affect the performance of my circuits? And in fact, as we see now with liquid cooling inside of PCs, there are techniques here, all of which may be required as we go towards the next decade of trying to keep Moore's Law alive.